Good morning, good afternoon, or good evening. This is going to be a full paper work through of the June 2022 Further Maths Paper 2. Ideally, to give you something to both help you review your own work, also pick out a couple of those useful exam techniques and hints on these questions. So, as always, we need to start by picking ourselves a humorous name. I'm going to be Ed X Cell or EdXL as my surname, as my name for this paper. So we'll jump straight in with the multiple choice questions first. Find the imaginary part of that. Now you can cheat slightly with your calculators. If you type that in with the complex mode active, you will get quite a nice answer straight away. Doing it by hand, we are just doing the rationalize the denominator style technique. And if we do expand it out and simplify, the imaginary part is 3. Question 2, find the mean value of the function between those two values. So mean value is 1 over the difference, the b minus a, if b and a are your limits, so it's a minus 0, between the limits of a and 0 of the function. Now you can't really cheat with this one because of that unknown upper limit, but it's not a particularly difficult integral to do. And we get 2a to the 4. Question 3, we have roots of the polynomial are alpha and beta. So the sum of the roots is negative b over a, and the product of the roots is c over a. We want alpha squared plus beta squared. And this is one of those identities which you should just have memorized. So this is p squared minus 2 lots of, so that becomes plus 12. You'll see they all got the p squared. It's just about picking out both the right sign and remembering it's 2 alpha beta you're subtracting off. Which of the following graphs intersects y equals shine at exactly 1 point? Well, if we think about what the y equals shine curve looks like, it's a stretched cubic. Now you do need to be a little bit careful if you're thinking about cosh. Cosh and shine don't actually touch. They do get really, really close together, but they don't touch, so it's not going to be cosh. Cosec, which is 1 over cosh. Well, if cosh was that, then sec is the one I've drawn here. 1 over cosh does indeed intersect at exactly 1 point. And if you do think about some of the others, cosec would have been that kind of shape that intersects twice. And koth, well, than is that, so koth would have been that kind of shape, again, intersects twice. So knowing your graphs here is the essential part. Into our actual questions, the multiple choice have been ticked off very quickly. Prove by induction that for all integers, the sum of the cubes is given by that formula. Okay, so I'm going to call this statement Sn, just so I can refer to it slightly easier later on. And let's do our base case. So our base case, we're trying to work out what S1 is, or by definition, that's the sum from 1 to 1 of our cubed is just 1. And we're claiming that that should be the same as that thing squared. So subbing 1 into that, we have half times 1 times 2, which is just 1 squared, which is 1. So therefore, the base case is true. And now we can do our inductive step. So we're going to assume that SK is indeed what the question thinks it should be. That thing squared. And we're going to then think about the SK plus 1. So SK plus 1 by definition is a sum from 1 up to k plus 1 of r cubed. But as is the norm for basically all induction questions, certainly when you've got summation, we're going to pull off that last term. The sum up to k is exactly our inductive hypothesis. And I'm just debating with myself whether I want to have that in its expanded form or keep the squared out. I think I want this in its slightly expanded form, which I am also going to put up here as well, because I'm anticipating some common factors to be expanded out. So that's by the inductive hypothesis. And if we carry on, we have that common factor of k plus 1 squared, but I'm also expecting to want a quarter outside as well, so I'm going to factor that as well, which is going to leave a k squared plus 4 lots of, and there's an extra spare bracket on that. Because it is a proof, I'm not going to try and do things too quickly, although I could have anticipated what that quadratic term would have factorized into. And then to make it 150% obvious, I'm going to write this in the way it's written in the question, with the k plus 1 split off and the whole thing squared as required. So I've done all the actual mathsy bits. Now I need to complete the proof. So by mathematical induction, as n equals 1 is true and n equals k implies n equals k plus 1 is true, then the sum to n is equal to a half n plus 1 all squared. Oh, if that bracket's in completely the wrong place. For all natural numbers n. I've kind of double stated the same thing there by saying n is in n as well as saying natural numbers n. A bit excessive. But you do need that full conclusion with those key phrases in it every single time. Okay. Really quite a nice proof by induction there. We didn't have to be too sneaky with any of the steps. Question 6, we have part of a curve y equals f of x. We have a tangent at the midpoint of A and B, and we've got points S and R and T and Q at various points. Sharon's going to use the mid-ordinate rule with one strip to estimate the value of the integral. By considering that trapezium, do we expect it to be an over or under estimate? So the first thing to notice is they've got us to draw trapezia, whereas mid-ordinate rule deals with rectangles. So let's build out the rest of that picture to be the rectangle that actually happens. And I'm going to call these new points V and W. So Sharon's estimate from mid-ordinate is going to be that rectangle, is the area VWRS. it's convention to label any shapes clockwise around the shape, is the area of that shape. But we can observe, and really I want to turn her estimate into this trapezia because the questions told us to think about this trapezia. So, but triangles VPT and PQW are congruent, i.e. they're exactly the same triangle. It's fairly clear to see that that side is identical to that side. They're both right angled. That angle is the same as that angle. So we've got a right angle, an angle, and a side rule for congruence. So these two triangles are congruent. So her estimate is also equal to the area of the trapezium. How do I want to label it? TQRS. So I've managed to translate her mid-ordinate approach into a trapezium. But now we can hopefully quite clearly see, and if I go for another color, that that trapezium is above the line here and above the line here. So is clearly an overestimate. The trapezium lies above the curve along the entire officially its domain, along the entire domain, so is an over estimate to the true area. By considering the area of the trapezium, state given reasons whether you would expect Sharon's estimate to be an over or an underestimate. I've stated I think it's an overestimate, and I've given my reasons by referring to that trapezium. And of course, the middle step there is making sure that you've shown that the rectangle and the trapezium are the same. A couple of quite wordy questions to start with. Not so mathsy, but a lot more words. Question 7. We have a function defined as so, and the graph has those asymptotes. Find the values of A and B. So this is checking you understand how asymptotes are created. So our horizontal asymptote is occurring when x goes to infinity. And in that case, f of x is tending towards, well, if x goes to infinity, the -5 and the plus b don't do anything. The x's can cancel, so it tends to a over 2. But we know that that horizontal asymptote is y equals 3, so a equals 6. This is only a 2 marker, so I'm giving way too much explanation to this. You'll get 1 mark for A, 1 mark for B. Don't really care about anything else. The vertical asymptote, though, I will give all the reasoning, is when the denominator equals 0, i.e. when x equals negative b over 2. But we know it should be 9 over 2, so b is negative 9. 7b, solve the inequality. Now, I'm a big fan of using the graphical method to solve any kind of inequality. Here, I'm tempted to use the multiply by the denominator squared. The only thing that's holding me back slightly is we are going to get a cubic. Now, that's not a big deal because we've got our calculators to solve cubics. So let's just do it that way. So the actual inequality we're trying to solve is 6x minus 5 over 2x minus 9 is less than or equal to x plus 2. And if you've forgotten the reason why we need to multiply by this squared, it's because inequalities, if you multiply by a negative, we'll swap the sign. So sometimes multiplying by 2x minus 9 causes a sign switch, which we do not want. Multiplying by the thing squared is always positive, so we'll never cause that sign switch. And again, I want to try and minimize the work I'm doing, so I'm actually going to move stuff around before I expand brackets out, because then I have that common factor of 2x minus 9. So I can move that thing over, factor the 2x minus 9, I'm going to be left with x plus 2, 2x minus 9 from what was there originally, minus the 6x minus 5. Now it's debatable whether expanding it all out and getting your calculator to refactorize is easier. I'm old-fashioned in regards to that. I prefer to let my algebra skills work harder than the calculator. Expanding this one out, though, I'm getting a 4x minus 9, which gets me to minus 5, minus that extra 6x. I've got minus 18, minus 5, that's minus 13. That looks like it factorizes really nicely. We want a negative 13 and a positive 2, which is going to come from that factorization. I'm just going to very quickly mentally re-expand that out, and it does get that quadratic. So now I've got my critical values. I've got the important points of my picture. And now, even though I didn't do a graphical method, we still need a graph in there. This is now a positive cubic with solutions of -1, 9 over 2, and 13 over 2. And we're looking for where this is above the x-axis. So I'm looking for that region and that region. I need to be careful because this one's special. That was an asymptote, so I can't actually hit that one. So it's -1 is less than or equal to x is less than 9 over 2. Can't be equal to 9 over 2. And x is greater than 13 over 2. So that is my solution set. And if you do in your calculator sketch them out, you can kind of see these values on that graph, at least approximately where they are on that graph. Brilliant. Moving on to, they gave you a lot of working space for this one. Moving on to question 8. We have a function f defined as sec. Okay, so this notation, this means that we have to differentiate it 4 times, which can be a little bit awkward. I am going to rewrite sec as cos x to the -1, and I'm just going to start differentiating. So my first derivative is going to be bring down the power, so we get -1, reduce the power by 1, and times by the derivative. Well, the derivative is sine. Now, if you do look in the formula book, you would have seen that the derivative of sec is sec tan. It's debatable whether writing it as sec tan is going to be nicer, because we're going to have to keep differentiating this. I'm debating it within my own mind. I think leaving it in this form, actually, it's still going to be really unpleasant. Is it worth doing this now as a quotient or as a product rule? This feels quite harsh for only 4 marks. I've got a feeling that I'm going to prefer to write this as sec tan, mostly because the derivative of tan is sec squared, and we now know the derivative of sec is sec tan. The second derivative though, let's do the product rule. We're going to have sec multiplied by the differential of tan, which is an extra sec squared, plus the tan multiplied by the derivative of sec. So the sec differentiates the sec tan, and we still have a tan left over. And again, I want to try and be as smart as possible before just slamming my head into even more work. So I'm going to very quickly recall the identity which links sec and tan. So from the normal Pythagorean identity, if you divide through by cos squared, you get that identity. So this is going to become sec cubed plus sec lots of tan is sec minus 1, sec squared minus 1. So this is 2 sec cubed minus sec. And I still need 2 more derivatives. So this is the main reason I'm trying to keep things as simple as possible so I don't have to worry too much. If I differentiate this one, bring the 3 down, we're going to have reduced the power by 1, but then times by the derivative. The derivative of sec, again, is sec tan. So my sec goes back up to cubed minus sec tan by differentiating the other sec. Again, it's worth at least very briefly thinking, is there any way this simplifies? Because they've got different coefficients, I could rewrite the sec cubed with the sec squared and replace that with tans, but I don't think that's going to be particularly nice. Any way we spin this one is not going to be nice. I could factorize out a sec or a tan, but that's going to be really unpleasant as well. Because this is the last layer, I'm just going to go for it. We're going to have to do 2 product rules on this one. For the first one, 6 sec cubed times by the derivative of tan. The tan gives us an extra sec squared. Or we could have differentiated the sec cubed. Now sec cubed we've already differentiated once. Sec cubed we're going to bring down a 3. The sec becomes sec squared, but then creates a sec tan. So that's going to be cubed x tan squared. And please do that slower if you're not convinced by that. Split it into its actual chain rule style components. And then the third term, sec times the derivative of tan, or tan times the derivative of sec. And we're getting as so. Now again, I could be tempted to try and simplify this as much as possible, but if you recall what the question wanted, it wanted this evaluated at 0. So I'm just going to sub 0 in and hope a lot of things just destroy themselves. So sec itself is 1 over cos. So 1 over cos of 0 is just 1. That's going to be 6 plus, or tan of 0. This is 18 times 1 times 0. So that term disappears. Minus, well, another 1 to a power. Minus 0. 6 minus 1 is 5, which is what the question wanted. And that feels quite harsh for 4 marks. There were some choices I made to try and make my life simpler in the way I rewrote some of these or adjusted some of these statements. Maybe if I differentiated straight from this stage, nicer things would have happened. I'm not convinced either way. But proceeding, hence find the first 3 non-zero terms of the Maclaurin for sec. So the Maclaurin expansion needs all of these terms. So we've got the first term. If I sub 0 into my first derivative, which is this one here. If I sub-zero into that, the tan just makes it disappear. So f dashed of 0 equals 0. F double dashed of 0. If I sub-zero into this one, I'm getting 2 minus 1, which is just 2. If I sub it into the third derivative, I'm hoping this one comes out as 0. The third derivative is this one here. Yep, both terms have a tan in, so both terms are destroyed. So that comes out as 0. And the fourth derivative of 0 is exactly what the question wanted us to actually do. So a lot of the work that we just did there, we needed to have done anyway. Now I am just going to pull up the Further Maths formula book because my memory on the actual Maclaurin, I've got a feeling it has a 1 over something factorial in it, but my memory is not strong enough for that. Okay, so I found the formula, and it does indeed have some of those extra factorial fractions in there. So it is straight from the formula booklet, f naught x f dash, that's x squared over 2 factorial, or just over 2, f double dash, and the pattern continues with the third and the fourth derivatives. Now it wanted the first 3 non-zero. The f dash and the f triple dash are both going to give you 0 terms, so they're disappearing. So the f of 0 is 1, plus the x term disappears, the x squared term, the 2's cancel, 1 plus x squared. The x cubed term disappeared. The x to the 4 term looks really unpleasant. It's 5 over 4 factorial, which is 24, x to the 4. And it does keep going, but all the odd terms, by look of it, are going to disappear. And all the even terms survive. Okay, part 8b. We want to find the limit of this expression. So we actually need the cosh. So let's create the cosh expression first. And one thing to notice is we are dividing by x to the 4. So the terms in x to the 5 and higher, when divided by x to the 4, will still have an x, will disappear. So you only need up to the x to the power 4th term. I'm just internally debating whether I want to create the cosh by doing the differentials, which is maybe simpler, or by writing it as the sum of 2 exponentials. I'm actually going to write it as the sum of 2 exponentials. So by definition, it's e to the x plus e to the minus x. So that's going to be half. The e to the x expansion is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial, etc. And I'm adding, if I were to instead do e to the negative x, which all it actually does is swap the signs of all of the odd powers. So minus there, plus there, etc. So that's going to be half of 2. The x's cancel. We've got 2 lots of a half x squared. And 1 over 12 x to the 4, etc. So that's going to be 1 plus a half x squared. That's 1 over 24 x to the 4. Okay, so now I can actually do the thing. So the limit as x goes to 0 of sec minus cosh over x to the 4 is going to be equal to the limit, and sec is what we had above. I'm a little worried that I have a half x squared and the other one only has an x squared. So in a moment, once I've written this down, I'm going to go back and check my previous working, because this feels like something wrong is going to happen. And I'm subtracting off, because I'd really quite like the x squareds to cancel so that we have just a nice fraction of x to the 4. So do I think my mistake is in my cosh, or do I think my mistake is in with my sec? And I've got a nasty feeling that this here is the mistake. So if I go back to f double dashed, yeah, if I sub 0 into that, f double dashed of 0 is 2 minus 1, which is 1, not, as I quoted up here, 2. So I'm going to change that to a 1, which means when I go in here, I do get half, which is what I actually desired to happen. And that thought process is exactly how you get rid of silly errors. When you think something looks off because it's not doing what you expect it to do, go and check, go and look for where that error could have come from. And now if I do that subtraction, the 1's cancelled, the half x squareds cancel. I'm left with 5 over 24 minus 1 over 24. I know I can simplify this, but I don't want to show off the answer too early. Plus dot 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 over x to the 4. And is this a proof question? It is a proof question. So I'm going to add a little comment to make sure that this dot 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 doesn't feel like we're hiding anything. So these are terms in x to the 5 or higher. Now, actually, if we looked carefully, the x to the 5 terms in both expressions don't exist. So actually, it's in x to the 6 or higher. But the important bit is bigger than x to the 4. So this is going to be the limit as x tends to 0 of the x to the 4's cancel. That's 1 over 6 plus, and again, I'm going to put that little comment on. So these are terms in x or higher, because I've cancelled out the x to the 4. So tend to 0 as x tends to 0. Putting in that little bit of explanation takes this from feeling like it's being fudged to showing complete understanding of the situation. And we get a 6th, which is what the question wanted. So I like to put a little statement as required at the end of these show that questions. Okay. Proceeding. Question 9. We have a very unpleasant looking equation, and I'm actually not sad because it's told us. It's told us that this isn't to go and solve it properly. This is a let's get a rough answer instead. So we have a point, and this is going to be my x0, y0, satisfies that differential equation. Use Euler's step-by-step method once, and then use the midpoint formula. The midpoint formula, if you recall, needs 2 previous steps, whereas right now we've only got 1, each with a step length of 0.1 to estimate the value. So my x1 is taking one step, will be 5.1. Y1, if you recall Euler step by step, is from that formula. So that's going to be the y0 is 12.3 plus the h steps we're taking is 0.1, lots of 5.1 squared minus 9 square rooted plus 2 lots of 5.1 times 12.3 over 5.1 squared minus 9. Really unpleasant, but we do have to write it out in full, show the examiner that we do indeed know what we're talking about. We're going to have to type this very carefully into our calculators. And I do unfortunately have a very old model which does not set up fractions particularly nicely. So an excessive number of brackets are needing to be used. Nearly there. I'm just going to take a quick double check that I haven't missed anything out. Make sure I've got enough brackets in all the right places. And my answer, this is claiming to be, is 13.449997. I'm going to write out my whole display here. Hopefully I can just use the answer button in a moment though. So that is my Euler step-by-step used once, then use the midpoint formula. So our midpoint formula is giving us the next values. So it's going to tell me that x2 is the next step up, 5.2. y2 is, well, y0. I've taken 2 steps down. You'll notice that that coefficient is a 2-step difference. y0, which was 12.3, plus 2 lots of h, with f evaluated at the previous term. So that's at the 5.1. I have noticed, which is highly unfortunate, that I have used the wrong values in here. So I've labelled this as x0, but then I've subbed x1 into the expression. So unfortunately, this needs fixing. I should just be subbing 5 in, not 5.1. Well done if any of you were screaming at that as a mistake. So this is a fairly easy fix in my calculator. I just need to go back, and every time I see 5.1, change it to just a 5. This might also make that number slightly nicer. Indeed it does. Because that 5 squared minus 9 gives you a 16, which square roots, whereas before it was not. Okay, so this does have an exact value, 13.46875. Okay, so now going forwards, and again, exam technique, I realised that I wanted to sub 5.1 in here, but I had a bad feeling because I remembered subbing 5.1 in here already. As long as you are almost hyper alert, those kind of silly mistakes get caught. If you're not hyper alert, then you're not really paying attention enough to spot them and to fix them. So looking back to the formula, I'm going back to this formula up here. I've got my 2 steps down for my y value plus 2 lots of h, and now I'm subbing in the previous x value and the previous y value, which is that 13.46. And here I'm going to use the answer function so that I don't need to type that in whole. It is going to be an unpleasant thing to type in, but we will manage. So now I've got the 5.1 squared minus the 9 square rooted plus an excessive number of brackets, put the answer in there, over 5.1 squared minus 9. Have a quick read through to check I haven't typoed into my calculator. And that's giving me 14.74016,345, which I'm then going to give to the question's requested accuracy to 6 significant figures, 6SF. Does that seem reasonable? It's very difficult to get intuition on a question like this. But yeah, it doesn't look bad. It's gone up a little bit. It's gone up a little bit each time. It looks like it's going up quite a lot because we're only stepping up by 1/10, and it's made about a 1.2 difference each time. Not much else you could try and, well, unless, well, the question does tell us to solve it, so we'll be able to get more intuition once we've actually solved it exactly. So find the general solution to the differential equation. So here come my fears. We now need to try and solve this thing, which looks exceptionally unpleasant, but maybe it all is just fine. So this looks like it's going to be an integrating factor style question. So I'm going to move that term over. The other choice we have is separating the variables, but there's nothing I can do to separate just that y that's locked in, certainly because this term here is just in the way. So we need to do our integrating factor. So our integrating factor is going to be e to the power of the integral of that thing. And it turns out incredibly nicely because that is just a derivative over an original. So my integrating factor is x squared minus 9. So if I multiply through by x squared minus 9, I'm going to get this thing. I'm starting to get a little worried because this side is now a power of 3/2, which doesn't seem to, which I don't believe integrates nicely. Ah, I've lost the minus. Aha, so I've lost. So again, I panicked. This thing is not doable at all. And if we do look back here, I'd lost that minus sign. So I'm actually integrating negative of all that, which means we're going to have negative here. So bring that power up, it's 1/x squared minus 9. I'm a little concerned that that doesn't feel particularly right. But it certainly makes one side of the equation a lot more doable. So multiplying through by our integrating factor this time, 1/x squared minus 9 dy by dx minus 2xy over the x squared minus 9 squared. And on the other side, I'm getting x squared minus 9 to the power minus 1/2. And that is an integral I know about. That's one of my either hyperbolic or trigonometric inverse integrals. So this side becomes d by dx of y over x squared minus 9. And if I did expand that out with the product rule, I'm hoping 1/x squared minus 9 differentiated will give me this term, which seems plausible. And yes, if you do spend a little bit more time thinking, you will get exactly that. So this is equal to, and I'm going to write this now as 1/the square root of x squared minus 9, because I know what I'm expecting now, Integrating both sides. That side is a simple integral, and I'm going to go back to the formula booklet to try and find the right form. This is the 1 over square root of x squared minus a squared. So this side integrates, according to the formula booklet, to cosh inverse of x over the a, which is 3, plus an unknown c. So y equals, and I want to write this in the nicest way, x squared minus 9 cosh inverse of x over 3 plus c lots of x squared minus 9. One thing that I'm going to notice really quick is the question told us what the domain was, x is greater than 3, which in here means that you're cosh inversing something bigger than 1. And if you know about the cosh curve, you know it can only be inverted when x is greater than, the input is greater than 1. So that gives me a good pat on the back that I haven't done anything overly foolish. I'm going to check that there's no initial conditions, but it did want the general solution, so I am going to pause there. The question does continue. Maybe it's to see, yep, comment on the accuracy to part A is the final part of the question. So given that y satisfies the differential equation, and yes, so we're now going to use those boundary conditions that the question gave us. So let's sub them in to what I've just worked out. So it's x squared minus 9 cosh 5 squared minus 9 cosh inverse of 5/3 plus c lots of 5 squared minus 9. So that's going to be something 16c. And this is where I find out whether or not this calculator has, and where it has, the hyperbolic things. Yes, it does. Brilliant. So cosh inverse of 5/3. We are wanting our answer to 5 sig fig, so I'm not worrying about it not being exact. I could try and make it exact by using the ln form of cosh inverse, but I'm just going to keep using the answer function in my calculator instead. So my c is horrendous, but I don't really care. I want to try and find the y value when I sub in 5.2 instead. So subbing in the 5.2 into that horrible nonsense is going to give me something. 5.2 squared minus the 9 cosh inverse of 5.2 over 3. And I still need to subtract answer lots of 5.2 squared minus 9. I'm hoping this gives, okay, that's miles off. So I was kind of hoping that this answer will be similar to the part part A, because here we used the approximation methods to solve this differential equation, and we got 14, and that 14 didn't feel terrible. But here we've solved it exactly, and we seem to imply that it should be 26. Oh, and I see what I've done. Okay, I've put this as a double negative into my calculator. So let's hope if I swap that to a positive, unfortunately I need to rewrite some of it instead because the calculator has lost the previous part of the answer. So I'm going to do it with, so I might lose some accuracy here. Yeah, I am going to, because I didn't write more than I didn't write enough significant figures here. And this is again another really good exam technique hint. If the question wants it to a particular significant figure, you should always be writing down at least one more significant figure than what the question ends up wanting it to be. So if I want this to be accurate enough, I do need to go back and recalculate some stuff. Unfortunately, that's because the older modeler calculator I have is not particularly good at going backwards and storing old information. So unfortunately, I am needing to retype in my calculation for C. And I am going to write those extra couple of significant figures in from that. 3298, 622887. So that if I do need to come back and check again, I can. So now I want to write in my new line with the cosh inverse of 5.2 over 3. And now I'm adding answer times 5.2 squared minus 9. And that is a much more sensible looking answer. Okay, that's giving me 14.74336,906, which the question wanted to 6 significant figures, 3, 4 to 6 SF. Okay, and now I'm much happier because that 0.7434 looks very similar to 0.7402. So comment on the accuracy to part A. So it is correct up to 4 significant figures. Both of those are 14.74 to 4 sig fig. So good accuracy. I would even say exceptionally good accuracy. 4 sig fig is more than almost any real life application would need. Okay, moving on to question 10. What appears to be a conics and graph transformations. We have C1 written in the normal hyperbola format. We have curve C2, which is not. So our first step is going to be to try and write both of these and make them look the same. At least put them in the same structure. So to do so, we are completing the square. So we're going to have x minus 3 squared minus 9 for the x minus 25. And I'm not going to try and accelerate too fast through y. I've seen enough mistakes where students try and do that too quickly. Let's leave the x as it was, minus 25. It's going to be y plus 4 squared minus 16. I'm swapping my brackets around a bit weirdly. So x minus 3 squared minus 25, y plus 4 squared. We've got a minus 9. We've got a minus 25 times minus 16 and a minus 416. I'm hoping that comes out to be a square number. Indeed it does. It comes out as negative 25. Now if I thought a bit more, I should have predicted it will be minus 25 because I need a 1 on the end and I've got this 25 to divide by. So let's do exactly that. Let's divide by the 25 minus y plus 4 squared equals, move the 25 over and divide by the 25, I get that. So now these two equations look very similar. We now can look what the actual changes were to in order to describe the transformations. So from C1 to C2, the x got replaced by x minus 3, and the y is being replaced. And we need to be a little bit careful because the y over 4, the over 4 has disappeared, but the y was being squared. So I replace y by 2 lots of y plus 4. Then I do indeed cancel the 4's out and make the y plus 4 that I was expecting. So to describe these, I kind of want to split this second one up as y, and I'm going to replace this with 2y and then replace the y again with y plus 4. So that implies that I need to do the stretch first and then translate by the 4. If I translated by the 4 first and then stretched, then I would get a different result. I'll get 2y plus 4 rather than what this actually is, which is 2y plus 8. So let's describe this. It's going to be a stretch vertically by scale factor a half. Remembering that in these further maths, everything is backwards. Stretch vertically by scale factor half. Then translate by, and we can put these together as a single vector, 3, -4, swapping both of the signs there. Okay. 4 marks, quite a lot of work to do for those 4 marks. Find the equations of the asymptotes to C2. Give your answer in those forms. Okay. And this is quite a common fact that they end up using. If you translate a curve, then all the key features of said curve translate in the same way. So the asymptotes of C1 will transform under exactly this change into the asymptotes for C2. So let's work out the asymptotes of C1 first. The asymptotes of C1 are y equals plus or minus b over a. The b is 2, the a is 5. Plus or minus 2/5 x. And then we're going to transform with x goes to x. Is it minus 3 or plus 3? X minus 3 and 2y plus 4. X minus 3 and y changes to 2y plus 4. And unfortunately, I don't think you should do these at the same time. So I'm going to split this into 2 questions with the positive and negative separate. So if I do the positive first, that's going to be 2y plus 4 equals 2/5 x minus 3. It wants it in the form all on the same side with everything integers. So let's make everything integers. I'm going to times through by 5 and divide through by 2. And that will be 5y minus x plus 23 equals 0 for one of them. For the other side with the negative, it's going to feel very, very similar, but we're going to get a negative sign swapped. 2/5 x minus 3 times up by 5, divide through by 2, but the negative makes this 3 minus x this time, so it'll be 5y plus x plus 17 equals 0. And those are my 2 asymptotes transformed from the previous asymptotes. Question 11. Find the eigenvalues and eigenvectors of that matrix. Okay, so sometimes there's tricks we can do. This is only a 2 by 2, so tricks are probably not worth it. So let's set up our characteristic equation. The determinant of m minus lambda I equals 0. So the determinant there, we've got our 5 over 2 minus lambda, 13 over 2 minus lambda on the diagonals. I've just put a minus lambda on those two. Minus, there's a lot of negatives going on, but a lot of them pair up. 5 times 13 is 65 over 4 for the constant term. We've got minus 9 lambda plus lambda squared minus 9 over 4. I am hoping that all of these fractions do dissipate. We've got 65 minus the 9 over 4, and that's just 14. This is making me quite pleased because that 14 can be written as 2 times 7, which gives me the 9 in the middle. So I've got my two values of lambda of 2 and 7. And now we need to find the corresponding eigenvectors. So when lambda equals 2, we're going to have 5 over 2 is 2.5, so that's a half x minus 3 over 2y equals 0. If I'm subbing into the m minus lambda I version, we need to equal the 0 vector. And negative 3 over 2x. 13 over 2 minus 2 is 9 over 2 minus 9 over 2y, or positive 9 over 2y. So that top equation becomes x equals 3y. The bottom equation, move that over, is x equals 3y. So let's pick, if I choose x to be 3, y can be 1, and there's an eigenvector. Of course, there's lots of, any multiple of that would also be an eigenvector. We also need to do when lambda equals 7. When lambda equals 7, 5 over 2 minus 7 is negative 9 over 2x minus 3 over 2y. The second one minus 3 over 2x, and 13 over 2 minus 7 gives me minus a half y. Simplifying each of those, that one, I'm going to be forced to have a negative, but then let's say that's y equals negative 3x. If I move the y term over and divide, and if I do a similar thing on this one, move the y term over and divide, we get exactly the same. So let's pick, if we choose x to be 1, then y is negative 3. So the eigenvalues and corresponding eigenvectors are given there. So let's just put it all together. When lambda equals 2, the eigenvector is 3, 1. When lambda equals 7, the eigenvector is 1, negative 3. Brilliant. The question does proceed. Describe how the directions of the invariant lines of the transformation represented by M are related to each other. Well, one of the key features of eigenvectors are they are the directions of invariant lines. So the directions of the invariant are 3, 1, and the way I used at least, and 1, negative 3. And you can work out quite clearly why that is the case. If you do m times one of these vectors, you just multiply up that vector. So you're just elongating or squishing along that direction, which is exactly what an invariant line is. The directions of the invariant lines are those, and if you haven't spotted already, which are perpendicular. Perpendicular. 3, 1 dotted by 1, negative 3 is 3 minus 3 equals 0. Those two vectors are perpendicular. So the directions of the invariant lines are perpendicular. Fully describe the transformation represented by M. So we have two invariant lines, 3, 1 and 1, negative 3, which are perpendicular, and their eigenvectors are telling you how you are pushed along each of those lines. So this is going to be a stretch by scale factor 2 along 3, 1, and stretch by scale factor 7. 2 and 7 were the eigenvalues along 1, -3. So this is a two-dimensional stretch by a different amount in those two directions. Quite a sneaky question to help you build towards that. Question 12. The shaded region is bound by the x-axis, the curve, and f of x. The shaded region is rotated 2 pi. Show that the volume of this solid is given by. So this is asking you to do that derivation to create the volume of revolution equation. And if you recall from notes, the way this is done is by considering little cylinders around the x-axis of width delta x, centered at x, with a height there which will be the radius of y. So then we can say that the volume is roughly equal to the sum of these cylinders, which are going to be, well, each cylinder has a height of delta x and a radius of y, so it's pi y squared delta x. I'm calling this function y equals f of x. As delta x goes to 0, this approximation becomes exact, let's try and use words in the right way, becomes exact, and the sum becomes an integral. So that means as delta x tends to 0, the volume becomes equal to the integral between those limits of a and b, becomes the integral of the limits of pi y squared dx, which, let's write it in the form that they want, is the integral of f of x squared dx. A useful derivation to make sure that you have memorized. We presumably now need to use this. In the case where a is 1, b is 2, and f of x is that nonsense, show that the volume of the solid is given by. Okay, 7 marks, and looks like quite rightly, that looks like a horrible integral that we're going to have to do, but let's just do it. So v equals pi times the integral between 1 and 2 of x plus 3 squared over x plus 1 squared x dx. So I've just subbed in what I want into there. Now I need to decide what my approach is. How am I going to tackle this type of integral? I'm looking for any tricks, but the only thing that I can see that looks relevant is going to be a partial fractions. So I'm going to set up my partial fractions. I'm going to expand out the numerator because I know that's going to be helpful later on. So I'm going to write this as a over x plus 1 plus b. Because it's a repeated factor, I need b over x plus 1 squared plus c over x. Multiplying up, I'm going to have the numerator there is equal to ax, x plus 1, bx, and c gains the x plus 1 squared. I like to pick clever values of x. So if I let x equals 0, 9 is equal to the a term disappears, the b term disappears, and the c term lives. That's just c times 1 squared. If I let x equal -1, and now I'm starting to regret that I expanded out that bracket. If I put -1 into there, I get 4. negative 1 into the A destroys it, and C destroys it, equals negative B. So B is negative 4. And finally, we've run out of clever values, so I'm going to compare the x squared coefficients. On the left, I've got a 1. On the right, I've got an A plus C. B doesn't contribute at all. So therefore, A is negative 8. There's a couple of negatives there, which makes me a little unsure. And so I'm sufficiently unsure that I do want to check a little bit more. If I look at the constant term, the constant is just going to be plus 9, which is actually what I got from just using x as 0, so that's not a helpful one to check. If I look at the linear term, that's going to come from ax, which is a minus 8, a bx, which is a minus 4, and the c, which gives me a 2x, is a plus 18. Yeah, minus 4, minus 8, plus 18 does indeed get me to the positive 6. So my slight worries of there being too many negatives actually just didn't matter at all. Okay, so now I can go back to v, which is now going to be the integral between 1 and 2 of negative 8, x plus 1 to negative 2. I've chosen to rewrite it that way because I know I can integrate it like that. Nope, that's the wrong term. It's going to be that a is over x plus 1, so I'm going to leave that as minus 8 over x plus 1. That I know is going to turn into a ln. This is the term, the b term over x plus 1 squared, which I'm going to write as to the power negative 2 plus 9 over x. I don't need a bracket there. So that is my partial fractions sorted. Now I can do my integrals. I still have this sad pi out in front. And let's turn everything into ln. So integrating that is going to be ln x plus 1. Increase the power by 1, divide by the new power, becomes 4x plus 1 to the minus 1. And the final term plus 9 ln x between 2 and 1. I'm going to glance at the answer. I'm feeling happy because I can see a lot of the things which are turning up. We just need to actually complete it all the way. So we've got pi lots. So let's sub in 2 first. That's going to be minus 8 ln 3. If I sub 2 in there, that's going to be plus 4 thirds. If I sub 2 in there, 9 ln 2. Minus, sub the 1 in, minus 8 ln 2, plus 4 over 2, which is plus 2, plus 9 ln 1, but that just is 0, so I'm going to not need to worry about that at all. Continuing, we're going to have, well, I've got a positive 8 ln 2, which I can write as ln 2 to the 8, minus ln 3 to the 8. I'm doing it that way because I know what the answer wants to look like. I've got positive 4 thirds and I'm subtracting 2, so that's minus 2 thirds. So this is going to be pi ln 2 thirds to the power of 8 minus 2 thirds. Is that how they wanted me to write it? Not really. They wanted the power written separately on the two terms. So let's do it exactly as they have requested. So that is pi times ln. Turns out the m and the n are identical. Was that really surprising? Probably a little bit, but it's not a problem at least. And we have the minus 2 thirds on the end. 7 marks there for quite an elongated integration question. 13a. Kind of glad that question 12 was over there. The matrix represents a reflection in that line. show that. You may use the result in the formula book. So as soon as it says that, I'm going to go and find the formula book and pull out exactly what it's telling me, so I know how to aim. So the formula book is telling us that if it's y equals tan theta x, then the matrix is cos 2 theta sine 2 theta sine 2 theta negative cos 2 theta. Okay, so I want to rewrite this, but with m's. We have m is tan theta. Okay, so I'm aiming for sine 2 theta and cos 2 theta in terms of this stuff. And things we can notice straight away that these are identical as we hoped, and these two are opposite signs, which is what we hoped. So I would quite like to show, so required to show that 1 minus m squared over 1 plus m squared is cos 2 theta. That would fix the top left and the top and the bottom right components. And I would quite like to show that 2m over 1 plus m squared is sine 2 theta. That would fix the off diagonal. So let's try. So the left-hand side is the much more complicated one. So 1 minus tan squared over 1 plus tan squared theta is what I'm dealing with. Simplest way to deal with that is probably to turn everything back into sines and coses, our normal technique. So let's multiply the top and the bottom by cos squared. So that's going to turn into cos squared minus sine squared over cos squared plus sine squared. And then we're basically done, because the numerator is by definition cos 2 theta. Denominator is just 1, which is the right hand side. So that one's done. Similarly, if we start with the left hand side of the other one, we've got 2 tan over 1 plus tan squared. I'm going to take the same hint from above. Let's just multiply through by cos squared. The numerator, one of the coses cancel, one of the coses survive. And on the denominator, we get the same as before. And surprisingly, it's not a surprise, we get exactly the same result. So therefore, reflection in y equals mx is, and it would have been the cos 2 theta sine 2 theta sine 2 theta minus cos, which we've just shown can be written as 1 minus m squared over 1 plus m squared, 2m over 1 plus m squared, 2m over 1 plus m squared, and negative 1 minus m squared over 1 plus m squared, which is equal to 1 over m squared plus 1 as a common factor, and the numerators left behind. Check I haven't done anything foolish. And we made it. Quite a nice little trick. That the grade, and actually the really fun trick is just this fact. The gradient of a line is equal to tan of the angle with the positive x-axis. Not really used as much as it probably should be. Part B. The matrix B is defined as that. Show BA squared equals a multiple of the identity matrix. Okay, so let's calculate some stuff. Let's work out BA as 3003 times by, and I don't really like using the huge horrible form that we have before, but let's do it. I put that in the wrong spot. So what was it? 1 minus m squared 2m m squared minus 1, which is going to be, I'm going to keep that factor out in front. 3 zeros, so that's going to be 3 minus 3m squared plus 6m, or just 6m and 3m squared minus 3. And then I really want to do BA squared, which is going to give 1 over 1 plus m squared squared in the front. And then I need to multiply this matrix by itself, which is going to be quite unpleasant, but we'll give it a go. We're going to get 3 minus 3m squared. This paper feels like it does have quite a lot of these fairly tedious expansions going on, tedious algebra going on. So that'll be my first component. My next component I'm kind of hoping will disappear entirely, so it's going to be 18m minus 18m squared from that times that, plus 18m squared minus 18m. Okay, good, that's coming out to be 0. The next component is 18m minus 18m squared plus 18m squared. Should these not be m cubes? These should probably be m cubes, should they not? Minus 18m. And the final setup is 36m squared minus... Why is it minus? That's just a plus, is it not? Yeah, plus... I've also made some sign errors elsewhere as well. Okay, so let's get rid of these. I think I was thinking determinants when I did those terms. So this will be 3 minus 3m squared multiplied by the 3 minus 3m squared. And this one down here is the 3m squared minus 3. That's why 3m squared minus 3. So this is going to be equal to 1 over 1 plus 2 m squared m4. And dealing with what's inside here, I've got 9 minus 18 m squared plus 9 m4. We've already observed that those components disappear to 0. Oh, I've missed the 36m squared. And down here, 36m squared plus 9m4 minus 18m squared plus 9. We're almost there. Let's simplify the terms in here. And for those who are ahead of the process, will have noticed that these things, well, one, they're both the same, but there are also 9 lots of the fraction out in front. So this is just 9009, which equals 9i. K is 9. Not a particularly satisfying question in any way. You might get away with doing some fancy tricks and writing this in weirder ways. I'm not going to trust it. I'm just going to stick with as it's written and do it as it's written. Part CI. The diagram shows a point P and the line y equals mx. Draw 4 lines on the diagram to demonstrate the result in part B. Okay, so BA squared tells you to do BA. So we can go to here, and that'll be AP. That's the reflection in the line y equals mx. And these are just rays out from the origin. BA, well, applying B is a multiply by scale factor 4. Then we're going to reflect back through the line. So that's A, B, A, P. And then we're going to multiply by 3 again, another scale factor of 3 pushing out. So this is BA, BAP. So that is the image point P dash. Draw 4 lines on the diagram to demonstrate the result in part B. Explain how your completed diagram shows P mapping to P dash has been scaled by factor 3 twice, i.e. by scale factor 9, which is the matrix 9i. Diagram shows that P to P dash, I could put little times by 3s on those. That might help the explanation, help me get those marks a bit more clearly. And more parts of question 3. The matrix matrix C is that. Find the value of M such that C equals BA. Well, BA was 3003 times A. So I can say that matrix A is the inverse of that, which is a third, 0, 0, a third, times by C. The opposite of scaling by 3 is scaling by a third, which is going to be 4/5, 3/5, 3/5, negative 4/5. And now I'm debating whether I want to do this in trig or if I want to do this in ems. Trig might be simpler, because then we're just solving that equals cos 2 theta, that is sine 2 theta. Have I convinced myself that I want to do it that way? No, let's do it with the m's. The m's might actually be nicer. So using the definition of A right at the beginning, we have that 1 minus m squared over 1 plus m squared equals 4/5. Which we'll try and solve. 1 minus m squared equals 4/5 plus 4/5 m squared. So that's 1/5 equals 9/5 m squared. So m squared equals a ninth. M is plus or minus a third. We're not sure which yet. And if we do the other one, 2m over 1 plus m squared equals 3/5. I don't actually want to solve this one because this will be a proper quadratic. So instead, I'm just going to use these. If m equals negative a third, I know this is the bad one, so that's why I'm doing this one first. This thing is equal to negative 2/3 over 8/9. Is that right? Yeah, that's getting nowhere close. Oh, it's 1 plus, that's why. The denominator was 1 plus. This is why you should always go back and look at previous pages. 10/9. So that becomes, times top and bottom by 9, that becomes -3/5, which is wrong. But if m is 1/3, it'll be 2/3 over 10/9, which is 3/5, which is consistent with the off diagonal, which means m equals 1/3. Matrix C is given by that. Find the matrix, find the value of m. Yeah, appears to all line up beautifully. Question 14, and this is the final question on the paper. On an isolated island, okay, this is our context-driven coupled equations. On an isolated island, some rabbits have been accidentally introduced. In order to eliminate them, they've introduced some birds of prey. We have X rabbits, Y birds of prey. We have our initial conditions here. When T is positive, the rabbits will reproduce at a rate of A% per year. And we are going to want to state the values of A, B, and C. So this one is my rate of change of rabbits. If I'm reproducing at 8% per year, that's from this term here. We're reproducing at a rate of 40% per year. So we're increasing, you've got an increasing factor of 0.4x. Each bird of prey will kill on average B rabbits per year. Well, that's going to be from this term. Each bird of prey kills 13 rabbits. And the death rate of birds of prey, so that's going to be the decreasing factor here, is C birds per year. That looks like 1.95. And the increasing rate of the birds of prey relative to the rabbits, number of birds of prey will increase at a rate of 1% of the rabbit population per year. So each of those four components in our coupled differential equations comes from each of those sentences. Solve the differential equations. And we want to turn these two differential equations into a single second order differential equation. So I'm going to start with equation 1 and diff it. So I'm going to get x, the second derivative. Yeah, I will use the dot notation. X double dot equals 0.4x dot minus 13y dot. And then we're going to use equation 2. So equation 2 tells me what y dot is. So it's 0.4x dot minus 13 lots of 0.01x minus 1.95. I have just noticed this is a 9-mark question, so we're going to have to do quite a bit here. That is now a second order purely in terms of x. So let's rearrange it to make it look like a second order differential equation. Plus 0.13x equals 13 times 1.95, 25.35. So now our auxiliary equation tells me lambda squared minus 0.4 lambda plus 0.13 equals 0. I'd quite like that to have been factorizable. Kind of sad that I can't see it being a nice one. So let's go to our polynomial solver. Let's put in our coefficients. If this does come out particularly horribly, it does say no real roots. Does this calculator have it does have a complex mode. Okay, so our solutions are actually really quite nice. 0.2 plus or minus 0.3i, which means we're going to get quite unpleasant solutions here. So the general solution is going to be e to the 0.2t a cos 0.3t plus b sine 0.3t. And that's my complementary solution. Yeah, that's my complementary solution. I'm also going to need to find my particular solution. So I'm going to let xp just be a constant, which means 0.13c equals 25.35, which means c is, let's hope that is a nice multiple, 25.35 divided by 0.13 is 195. I probably could have predicted that because that's where it came from. So my general solution is going to be e to the 0.2t a cos 0.3t plus b sine 0.3t plus 195. So now I can try and find and use my initial conditions. I do still need to find my y. Do I want to do that before or after I start playing with things? I probably want to do that before. So I'm going to use equation 1. I should differentiate it first because I'm going to need the derivative of this. So my x dot is going to be e to the 0.2t times the derivative in here, negative, plus 0.3 b cos 0.3t. Or I could have differentiated the e term 0.2b sine 0.3t, gone outside the box slightly. The 0.195 just disappears. And then equation 1 is telling me that 13y is equal to 0.4 minus is 0.4x minus x dot. So 13y is equal to, and I'm going to put the number at the front just because that's easy to deal with, plus e to the 0.2t. And now to try and deal with all the coses and sines. I almost feel like I want to try and factor it all in immediately. So I have 0.4 lots of that. And I'm subtracting for the cos term those two. So I'm going to have left over 0.2a minus 0.3b cos 0.3t. For the sine, I want 0.4 of that. And I'm subtracting those two terms. So I'm going to have 0.2b plus 0.3a sine 0.3t. Okay. And of course, I should divide that all by 13. 78 is a multiple of 13, is it not? Yeah. Do I want to do that straight away? No, I'll leave it like that. So now let's use our initial conditions. When t equals 0, there is 1755 and 30. X is 1755 and y equals 30, which is going to create us a couple of equations. So the 1755 when t equals 0 is going to leave behind an a, the b disappears, plus 195. So a is 1560. And from the y, 30 times 13. 390 equals 78 plus. Now again, the e term becomes just 1. The sine term disappears entirely. The cos becomes 1 plus 0.2a minus 0.3b, which is going to solve for b. So 390 minus the 78 minus 0.2 times 1560 all gives 0. So b is just 0. That is awfully pleasant. Okay, so let's write out our equations and then we'll check whether they do actually hold, because I'm definitely slightly suspicious of that fact. So going back to our x, which is at the top of this page, we know what the a is, e to the 0.2t cos of 0.3t plus the 195. Let's quickly check that. Yep, at t equals 0, that does indeed give the 1755 I want. And the second equation, I'm going to have to divide through by 13. We think the b is 0. Let's hope that each of these coefficients do indeed divide by 13 nicely. So it's 0.2 times 1560 divided by 13 gives me 24 cos 0.3t plus 0.3 times 1560 divided by 13 plus 36 sine 0.3t. And if I do sub in t equals 0 into that, I get 6 plus 24, I get the 30. So my initial conditions are at least correct. Again, you'll have to check this very, very carefully in an exam situation. But I trust, other than a silly error, most of that working. Let's check I actually answered the question. Solve the couple differential equations to find both x and y in terms of t. X and y are in terms of t. Beautiful. Given that x and y are both positive for the first 5 years, show that your answer to part B will succeed. So we need to go all the way back to the context. What was the conservationist plan? In order to eliminate them, they've introduced some birds of prey. So we're trying to eliminate these rabbits. So so we want to make x be 0. So let's see if x ever became 0. So we want x equals 0. i.e. 0 equals the x equation I've already forgotten, 1560 e to the 0.2t cos 0.3t plus 195. Let's check that 195 number was correct. Yep. Okay, so given they're both positive for that time, use your value, use your answer to show their plan will succeed. So if I do try and I'm a little bit worried because solving an equation with mixed exponentials and trig is officially not possible. So this is negative an eighth. So how can I show that this does indeed become 0 at some point? Now it doesn't become 0 before 5, but it might become 0 shortly after 5. So my feeling is actually a change of sign style approach. If I sub 5 in, so if I do e to the power of 1 times, and I don't trust this calculator, so I'm putting extra brackets in, times cos of 0.3, add an eighth would be positive. And if I choose a slightly later time, so if I sub in maybe 6 years later, oh, I didn't put that in. that's still positive. When I subbed 5 years in, yeah, it didn't change much. So really, I want to show at some point. Yeah, I really just want to show. I want to say that I want to show that x is at some point negative, which will then mean there's a change of sign, and therefore at some point it was 0. But the awkward thing is that 8th coming in. So let f of t, and I am going to go for this change of sign style approach. Let f of t equal that. Then f of 5 is, it's going to be some positive number. F of 5 is 2.8, which, no, that's not that promising because I've divided through by stuff. I was going to say that's promising, there's only 2 rabbits left, but that's not what that means. So let's try some number of years later. And really, I'm just going to keep trying later years till I get a negative number, which at the moment doesn't seem like it's going to happen. So let's think about the cos curve. The cos curve starts at 1 and the cos curve goes negative at pi by 2. And then it goes positive again at 3 pi by 2. Now that's awkward because that's still in the 0 to 5 years. There wasn't a negative anywhere. Because this is worrying, because this is implying that it's kind of exponential growth. It's living up to an exponential growth style setup. So in the super long term, the rabbits will go off to infinity. It's just, do they get negative first? So that range there is about 1.5 to about 4.5, which we're told it's always been positive. So that's no good. I want to go a bit further. So that's 5 pi by 2, which is very roughly 7.5. So if I sub in 8, that's still positive. Oh, I want to kind of hit 8. Because these are, that's equal to 0.3 times t. So that point there is very roughly where t was 5. So the cos term should, am I just in the wrong mode? Yeah, I'm in degrees, that's why it's not working. We have to be in radians. So now if I sub 5 in, and when I sub 6 in, it should just work. When I sub 5 in, I'm 0.556. If I sub 6 in, it does get negative. F of 6 equals negative 1.54, which implies f of t equals 0 at some point. Should be starting to be sad because it's been on for so long. At some point between the 5th and 6th year, i.e. the rabbit population was eliminated, which is what the conservationists wanted. So given they're both positive from that range, use your answer. So we wanted it to be equal to 0. So we set up, and I could have actually just subbed in 5 and 6 into x rather than into this adjusted f of t instead. I kind of got hung up on the change of sign idea and tried to simplify my equation first. Didn't need to do that. But the change of sign did end up working. Okay, and that is the end of that paper. Of course, in a real thing, you would want to spend some time now going through and checking very carefully, looking for those things which didn't feel right that you couldn't fix immediately. You'll notice that we did spot quite a few little errors while doing this paper that we managed to fix at the time. None of the rest of the paper felt obviously wrong. Doesn't mean that this is perfect. And if you do find any errors in this, please do let me know, and we can try and fix them. If you have any further questions from this, from your own working, whether or not you get certain marks or whatever it might be, please do ask. And hopefully that was quite a helpful process. So enjoy the rest of your days.